All right, so I guess we just start. So thank you very much for sticking around and for being willing to listen to a biologist talking to a bunch of computer scientists. I suppose you're computer scientists, so anyway. But I will talk about insect brains and how they relate to what you guys are doing, I think. And the reason I'm here is probably this thing. And I'm a biologist, so I have to look up what Moore's law actually is, right? But you're probably all familiar with that, but computer performance has doubled every 2 years for the last 50 years or so. But the problem is it's not going to last forever, and when I kind of Google this kind of stuff, what I can kind of come up with is this kind of statement here: as transistors reach atomic scale and fabrication costs continue to rise, the classic kind of technological driver that is underpinned like Moore's law for more than 50 years is failing and is kind of anticipated to flatten in 2025. I don't know about the year, maybe it's going to be 5 years later, but in the end what you can see if you look at this kind of stuff is that, well, all these curves that have been rising for so long will all flatten out after a while. It doesn't really matter what exactly is on the curves here, but the kind of technology development will not go on forever in the way it has been for the last 50 years or so. And that's going to be a little bit of a problem if we expecting it to happen like we think. So what we have currently is this CMOS technology, right? So it's a general purpose computer so we can do everything with. And they cannot meet the demands of the future. So what we have to do is think differently. And in this paper that I found, basically it was summarized that there's kind of 3 ways one could do, right? So we could try to make what we have a little bit more efficient in making kind of packaging a little bit more kind of maybe more denser, go 3D, things like that. Or you can have new materials. Or, and that's why I'm here, essentially you can try to develop completely new computational architectures. And some obvious things that are happening at the moment are essentially quantum computers and also actually neuromorphic stuff. And so neuromorphic computing is what we are developing. And that's what I want to talk about. So how can we actually develop radically new architectures to do computing? And one thing we can do that also will address this issue here, and that is energy efficiency is extremely important, right? So if we consider how much energy AI is actually consuming at the moment, that's clearly not sustainable. And what we have to do is find ways to do computing a lot more efficiently. And I'm a biologist, right? Sorry, one possible solution is to take inspiration from biology. And so essentially, what the goal is of what we're doing in our research is we're trying to reveal the computational algorithms that make brains efficient and then try to develop matching computational architectures. So let's dive a little bit into biology, show you some pretty pictures of birds and things like that and insects. But I just want to make the point here that if you put a camera on a bird and you let it fly through a dense forest, it does extremely well. Right? So this is super fast movements, and it does it all in real time with a little bit of energy, right? So it can deal with obstacles in real time extremely well. And basically all animals are really good at what they're doing. If you have a bat or you have a dragonfly or a flying fish or a bee, they really have amazing brains that sense the world and control the body in real time. And if you consider the example of a bee, it does it on a few drops of nectar. So they're really, really good at what they're doing. And also, actually, the body is optimized to interact with the world in a fantastically efficient way. So what if we try to use technology to mimic that? So what we have here essentially is the fact that animals are extremely energy efficient, fast, autonomous agents that really dynamically interpret the sensory input from the world and generate steering signals in real time. And that's basically what we're trying to do in autonomous cars, in drones. I mean, these are obviously not real drones, but kind of the thing we imagine to take over the world with at some stage. But the thing is, can we match what animals can do with our current technology? And the answer is, well, not so well, actually. So if you send drones into a forest and let them forage and let them fly around, they don't do very well. And where they can do it, like the very, very latest versions of them, they can do it, but it's extremely energy inefficient. They have very complex sensors, huge batteries, and they're not truly autonomous. They don't really know why they're doing what they're doing, right? Opposed to animals who make decisions on their own, truly autonomous, they have a purpose, right? And drones don't. So that's a few of these biggest differences. We're trying to take inspiration from that, and basically we can take inspiration in two different ways. We can use their brains to see, okay, how does the control system work to control the animal? And then we can also look at actually the body. So how does the physical structure of the body optimally interact with the environment? And so both things can serve as inspiration for actual technology development. I'm going to focus on that part here because I'm a neurobiologist. So I'm going to look at the brains of species and see what we can learn from those for applying that to actually computational architectures. And the goal here is really to harvest the results of 500 million years of evolution to gain energy efficient and intelligent technology. And having shown you these drones that navigate through forest and comparing that to the bird that flies through the forest, I think navigational decisions is a really good starting point because it's simple, but it's very difficult, right? Excuse me. So essentially, when we look at the brain, that's a human brain, and what is a decision, right? How do we do what we're doing? So if you simplify what brains are doing in general, we can say that we take information from the environment through our senses, and we create something like an internal representation of the current state of the world. Then we compare that to a desired state of the world. How do we want the world to look like? And we take into account previous experiences, motivation, and our behavioral state for that. And then we compare the two. Now, if the two don't align, we do something about it. That's called behavior. So any mismatch between the current state of the world and the desired state of the world will be leading to some kind of compensatory action. Now, this is all really abstract, very fluffy, but it turns very much more concrete if we look at that in the context of navigation. But before we do that, we have to realize that we do this with 85 billion neurons in our brain. That's quite a lot. Maybe not so much as the transistors you have in your chips, but it's still a lot of neurons. And each of them makes on average 10,000 connections with other neurons. So that's more connections in the brain than stars in our galaxy. Anyway, if we simplify the problem a little bit and focus on navigational decisions, then these fluffy terms, current state of the world and desired state of the world, they turn into the current heading and the desired heading. And that's much more simple because both of them are angles. And all you have to do if the direction in which you want to go is not matching with the direction in which you're actually going, you have to steer, right? You have to turn right or left. That's all you have to do. But it's a big part of what we're doing and what drones have to do and what any autonomous agent will have to do when they fly through the world and try to navigate autonomously. The problem is we do this maybe not with all 85 billion cells in our brain, but with a very large portion, with millions of neurons are required to solve this problem. So what I do is I don't look at the human, because that's the number, right? I don't look at the mouse either, because they've still got 70 million neurons. But you see the little blob there, which is probably not even brain-shaped, but that's an insect brain, right? So it's really small. And so the numbers of neurons we have in insect brains are between 100,000 and 1 million. And if you zoom in, they're still pretty complex. Probably some of you haven't even realized that insects do have brains, but they do have brains, and they're pretty amazing, and they're very complex, and they make decisions. Essentially, they have to solve the same problems that we have to, just in a bit of a simplified version. And so you have very, very complex brains, but numerically, they're really simple, but they're complex enough to be interesting. So that's why we're looking at those in our work. So just to convince you a little bit more, to show you some colorful pictures that you probably haven't seen in this computational conference, I suppose. This is butterflies, right? This is monarch butterflies. They fly 3,000 kilometers across an entire continent to pinpoint a tiny little mountain top in central Mexico. And they fly that without any GPS, any kind of technology. They find their way. They do it only once every 3 generations. The same happens here in Australia with these kind of brown moths. They fly 1,000 kilometers to stay in small alpine caves, and then they fly all the way back to breed again. And then they die, and the next generation does it again. So they have to find a way with a brain that's the size of a grain of rice, essentially, and with a few drops of nectar as energy supply. Try to do that with a drone, and it will crash and burn very, very soon, or it will use up vast amounts of energy. The other thing here is, like that's my final example, is this little bee that lives in the jungle of Panama, and it lives in little sticks, right? And finding a little stick in this jungle is really hard, and to make it even harder, it does it at night when we can't even see the hand in front of our face. And so these tasks are really difficult and a very complex environment, and all really done with a tiny little brain. So, how can we look at those brains? So we can basically, first of all, simplify the problem again a little bit more, because if you look at navigation, every navigational task essentially consists of these very basic decisions that you have to do. Essentially, at each moment in time, depending on where you are here, you go out on your hive, you go on a convoluted journey, you find food, and you go back home. But at each moment in time, what you have to do is you have to check, okay, where do I want to go? What's my desired heading? What's my goal direction? And where's my current heading? And if the two don't match, you steer. That's really all you have to do. So let's look at this in the brain. Where do we find the neurons and the circuits that are computing these kind of things? So what we have here is a 3D reconstruction of a bee brain, and in the middle there's this little green area called the central complex. And that area is what does everything we realized was needed for making these navigational decisions. So basically what we have here is an internal representation of the current heading, we have an internal representation of a goal direction, and we have a steering center, everything in one brain area. And the cool thing is it only consists of about 3,000 to 5,000 neurons. We can actually look at that in detail at synaptic resolution and try to see how does it do this computation. Can we learn something from that for implementing it in technology? So essentially, the cool thing on top of that is that it exists all across insects. So these are the brains of like a butterfly, a locust, a bee, and a beetle, and a moth, and a little like wasp, and so on. So every single brain looks very different. However, it always has the little green bit in the middle, which is this central complex, or the central like navigational decision-making center. And that's amazing. But there's a big problem here in that we have 1 million species of insects in the world. They have a vast variety of behavior, and everybody has the same little circuit that controls it. So how is that really possible, right? And so that's where my research is really focusing on from the biology side in this point. So we're asking, after 450 million years of evolution, how conserved is that brain region really? And how has this circuitry evolved? And can we find things that are shared across all species? Because these will be the things that are important if we want to mimic this whole system with technology, right? So we want to follow the central decision-making center through the entire 450 million years of insect evolution. So how do we do that? We're basically extracting the computational hardware of the brain, like directly. What we do is we get out the brain of an animal, we embed it in some form of plastic, we place it in the vacuum chamber of a microscope, and then we have a microtome that's inside the vacuum chamber that slices off slice after slice of this tiny little brain, and we use an electron beam to scan the surface of that brain slab, essentially. And so we're accumulating image after image after image, so in the end we get about 8,000 images at synaptic resolution of these brains. And so that looks in the end something like this. So if you zoom through a brain, that's how it looks. If you really zoom in far enough, that's how your brain will also look if you zoom in far enough. And from that we can then extract what neurons are actually there, how do they talk to each other. So when you do that, with lots and lots and lots of students' help, you can extract this ball of spaghetti from the insect brain, essentially. This is about 1,800 partially traced neurons, and we can start to develop ideas for what are the circuits that actually make those navigational decisions. So when you do that, you find some stuff that's always the same, right? So this is a circuit that is involved in encoding the current heading of the insect. So this is a bunch of neurons that act as a ring attractor, and that essentially creates a bump of neural activity that moves when the animal is turning around its axis, right? So it's basically like a little compass needle in the brain that actually can actually decode where the animal is facing within its environment. And if you look at these neurons that do that across 6 or 5 species of bees and ants, and compare that to the fly, for example, which is here, it's always exactly the same. So the same number of neurons across about 350 million years of evolution. So if you want to build a head-direction system that controls a drone, this is probably a good way to do it because it hasn't changed for 350 million years. So the organization of this system has remained identical for all that time. But there's also things that change between species. So it doesn't really matter what these cells are. I mean, they're quite beautiful, I think. But what you can see here is that the yellow neurons, they're there in all insects. However, the blue ones are only there in bees. And we think they're doing very specific that we think is kind of a feature that only bees have in terms of the sophisticated navigational abilities. So we find two things. We find things that are always the same, and we find things that are very different across species. And that makes it interesting because then we can use that to extract actually information flow between these like anatomically like identified neurons. So what we get is these kind of connectivity graphs. We can see, okay, which neuron is synapsing onto which other neuron, and then we form circuits, and we can deduct which pathways are there for information to be processed, and where are those decisions made that we want to understand. And so we can then build that into simulations, and they can either be basic kind of models of everything that is always there, like the shared basic components of the brain. So if we want to start to build something in technology, that's probably where we should start. But then we can also say, okay, if we want to have specialized devices that do something very specific, like flying through a forest or doing long-distance migration, then maybe we want to mimic what we saw in the moth, or in the butterfly, or in the bee. But anyway, so let's start a little bit with what we've actually done so far. So this is now moving from biology into the technology, just in case you got impatient with the biology at this point. But when you take the actual connectivity of all the neurons that we now find in this brain area, so this is a generic kind of representation of that. This is all the neurons, it's drawn out as lines essentially, and you plug that into a computer, into a kind of a force-directed graph diagram, you're getting the underlying circuit topology. So these two things are identical. They're exactly the same stuff. It's just that it's kind of arranged in a way that like reveals the underlying logic. And that's pretty amazing because what you can see here is 3 concentric rings that are kind of wired up in this really kind of intuitive way. And what this neuron, basically what this circuit can do, we can see in a little bit. And we think, so basically what we have here is 3 concentric rings. So the inner one is essentially what I talked about, is this kind of internal compass needle, right? So it creates a bump of activity that moves around this ring whenever the animal turns around its axis. The second ring is a memory layer that actually tells the animal where it's been for the last couple of hours or so, and that stores that information. And then whenever the animal wants to go back home to where it's kind of originated, it can compare the activity in this ring, where it's currently facing, with the activity in this ring, in the orange ring, which is where it wants to go, because that's where home is, right? And then it can use the blue neurons to steer back home. That's the theory, and if you place a bee in a simulated environment, or I mean, you place a simulated bee in a simulated environment, but only using this thing as its brain. What you can do is you can see what it does. You can send it out on a random journey, and you can see that, okay, whenever the bee faces in one direction, this kind of activity moves in one specific direction. And here's home, and you see that over time, activity accumulates in this region over here of that ring, which is exactly where home is. And then, at some point, you let this circuit do the steering, and that was here, the green line there. And then you see, oh well, it actually does pretty well. It does go exactly where home is. So just using these few neurons, and this is just a handful of neurons really, you can create a homing kind of mechanism that is extremely efficient. The thing is, we haven't programmed in a stopping signal, right? So it overshoots, but then it does something quite amazing. As soon as it overshoots, because the system is still running, it soon starts to actually go back, and it circles around home, which is exactly what insects do when they can't find home. When they go to the area where home should be, but they don't really see the nest, and they start to do exactly what our model has also done. So it's an emerging thing that we didn't actually program in. So that is what that model does in theory. We can also place it on a little robot. It's a very primitive robot. It's just a phone on wheels, essentially. And what we can do is we can also send it out on a random journey in the real physical world. And that's a bit challenging because you have very noisy input, using the real information to actually that you have in your environment to estimate speed and things like that, right? And so you see that there's some really bright objects there. There's actually people walking by. So this is I think a gym, something in like the University of Edinburgh. And so, but at some stage, after this convoluted outbound journey, you then let the animal or this kind of robot decide where is home, right? Excuse me. And then it does actually go home. It doesn't go directly, but it does this kind of meandering movement. And now if you look at insects, that's also what they do. They always do this kind of oscillations, and that's also an emerging thing that we get from this system here. So with this very simple system, you're getting an extremely nice homing circuit, essentially. And that then caught the attention of somebody at Nanolund. And they come from a very different background. They're actually kind of looking at nanowires and building solar cells and trying to use these kind of components for making neurons, artificial neurons, and actually building something more meaningful or something more interesting than just light absorbers. So, and that is basically, this is what I want to talk about for the rest of the talk, essentially. And so we have this really simple model here, just consisting of about 50 neurons, and we know exactly what it should be doing. So this is something we can actually build, right? Because if you're trying to build something from the human brain, it's really, 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 really difficult because you have so many neurons, you don't know where to start, you don't know when it actually works because you don't have a good readout, right? So what each of these neurons in this model actually is doing is simply just an input-output function, right? So you have a few inputs, some of them are excitatory, some of them are inhibitory, and then you have an output, right? And it's just a little transfer function. And, well, can we mimic something like that with some kind of completely novel hardware? Of course, you could really build that with transistors very easily, right? But we try to do this in a different way. And what we're trying to do is we're trying to use nanowires. So nanowires are these tiny little 200 nanometer long grown rigid structures that can be used for all kinds of things. For example, solar cells. So they're really good for light absorbing and for also light emitting, right? And that is what brought us to the idea that maybe we can build these neurons with nanowires and to use light to communicate between them. Right? So what we're currently always doing is we use electrons and we use wiring and things like that, but we can predict how light moves, right? Or actually how it spreads between components. And so if we use that in the right way, we can probably save on the wiring. And that was the initial idea to how maybe we can make this very energy efficient in the end. So to basically replace electrons with photons. Well, we started simulating the whole thing, and so that is actually the first prototype of like a nanowire structure that we thought of. And so essentially you have this kind of T-shaped kind of nanowire which has two regions of absorbance and actually one kind of LED, and the whole thing is just a few nanometers or like maybe a few micrometers across. And then the idea is to mimic this internal ring of this ring attractor circuit that we've seen, right? So actually the compass needle. And the interesting thing is that in this ring, every neuron has to inhibit every other neuron. And it has to inhibit the one on the opposite side of the ring most strongly, and has to inhibit like the ones on where actually its direct neighbors least strongly, essentially. So you have this graded strength of connections. And that seems, well, we can maybe do that with light, right? So when you place all of these kind of T-shaped artificial neurons in a 2D light guide and arrange them in an actual physical circle, then you can model how the light is spreading through this 2D light guide. And if you do that, essentially it looks like this. So you can't really see these components here, but they're there, but you can model with a physical model. I can't do that, but all the physicists can do that, how light is spreading through this system here. And you can then see that the light is reaching these guys on the opposite side of the ring most strongly. and it's barely kind of touching the ones on either side of it. So essentially what we have is a simulated connectivity matrix that is very much resembling what we have in biology in the model, just by spreading or by actually modeling how this light is spreading. So the big thing is that we're using the geometry of the nanowires to do the computation, because the computation that we have here is essentially a ring attractor. So it's a very complicated thing, really, but it's very simple to actually build that with this kind of technology, or you can simulate it with this kind of technology. So that's the take-home message at this point, is that the geometry of the circuit determines the implemented computation. So it can only do one thing, but it can do that extremely well. So, but then does it work, right? That's where it gets a little bit more challenging. So what we have here is the circuit that you've seen so far. And what we did to make sure that, well, can it even work? We did some more simulations. We essentially kind of embedded the simulation of the nanowires into the model that we had previously and try to see, does the animal still go home? Does the model still work? Using nanowire simulations as the central kind of compass part. And it can. So you see on the outbound journey, this is a random journey, and then at this point we say, okay, please guide the animal back home. And it does it quite well, as kind of good as the original model. So in theory, it works really nicely. So now we got 3 million euros from the European Union to actually build a prototype for this kind of thing. We're not quite there yet, but I can give you an update as to where we are at this point. And it's pretty promising. So the challenges are, of course, that nobody can build a T-shaped nanowire. That's problematic because it's really hard. We can, but it's really hard and really complicated. And what the new design looks like is a bit like that. It's a bit more complicated, but actually it's much simpler to build because everything you need is linear kind of nanowires, and you can hook them up with like little gold bits and so on. That's all not my expertise, but the physicists are doing that. And so when you look at this is actually feasible. And what the update is, we currently are able to have two nanowires talk to each other with light. That was never done before, and it works. And that is really amazing. So we don't use arrays, we use single nanowires to talk to one another, and it works. And so the publication is in the making. So I can't show you any raw data because it's a bit, we can't show it too well. But anyway, so the thing is, though, that we have this is very feasible. The next thing that we have to do, though, is a little bit more tricky, and that is, well, you need memory, right? And any computer needs memory. So what do we do about that? How can we put memory in this system of nanowires? Because it's all instantaneous. It just really talk to each other, and whenever you switch off the light, it's gone. Somehow you have to implement the memory in this. And well, there's two strategies we can use. So the neurons that we have in this model, they were just basically abstract integrators. We didn't really worry about trying to implement the actual kind of mechanism of the memory. But there's two strategies we can use for actually building memory within nanowires. And the one is actually directly embedded here, in this new design. So you have this little bit there, which is essentially a little capacitor, right? It's tiny little, small, and but what we have here is a very short period of time. You can store charges within this little capacitor, and then you can actually gate it, and then it will drive the light emission in this LED there. So you can store information for pretty short periods of time, a few milliseconds, but it's very useful if you run this whole thing very quickly. However, if you want to run a navigational device in real time, you need memory over maybe many hours, and this thing doesn't last for many hours. So how can you do that, right? Without having a hard drive attached to it, which is clearly what we're not wanting to do. So what we can do is we use photo-switchable dyes to implement a biologically inspired memory. So let me walk you through that. So initially what we have is we have one nanowire that emits light, and it's actually talking to the other one that will also emit light. So that always happens instantaneously. But what you can do is you can put an opaque dye in between those things, within this light guide where everything is located. And then, well, that blocks the light, absorbs the light, and this one can't emit light on its own. But what happens over time is that when you illuminate this photoswitchable die, the more you illuminate it, the more transparent it becomes. And at some stage, it will be transparent enough to drive that second neuron, right? And so what we have here essentially is a kind of illumination-dependent memory, right? So the strength of this connection depends on how much it's been used. And this is exactly what memory is in a biological system, right? So basically you're rerouting information according to where it's used a lot, right? And stronger connections and weaker connections is all that we do in our brain. So we don't have a separate storage. We're just changing the weight of synaptic connections to acquire information and to store information, essentially. And that is what we can do here as well. And so we have these photoswitchable dies as a weight-based memory that we can actually embed right where the computation is happening. So there's no separation between computation and memory. It's all happening in the very same place, just like in a brain, essentially. So this is really what biology is also doing. We're trying to get inspiration from that. And so the update here is where the dies are done. We have them. They last for many days. We can tune them to last for maybe minutes, hours, or days, or are truly permanent. And we can reset them by just heating the whole thing up, and it all works really nicely. Now what we are currently doing is trying to see how they interact with the nanowires. We don't know that yet, but it seems also very promising. We can encode nanowires. We can embed them in the matrix of this 2D light guide, and simulations of the whole system seem to suggest that this kind of memory, the actual dynamics of these photoswitchable dies, are actually suitable to make this whole circuit work. And that's another advantage, again, of this whole circuit, because we know exactly when it works, right? So we have a really good benchmark, because when the animal gets back home, we know it worked, right? And so that's really easy. So there's really good metrics of actually doing that. So if that memory wasn't good enough, it would fail. And there are some challenges in that, but in principle, it works really nicely. So, to summarize a little bit, the advantages of our nanophotonic circuit are basically, well, first, what I just talked about, it contains less than 100 neurons and does something useful. It does homing, right? So we know when it works, and we can realistically build it as a proof of concept. But obviously, we don't want to get stuck with just this tiny little navigation circuit. But it has a few properties that are really, really useful, in actually the context of what I said in the beginning. And that is there's no separation between memory and computation. So it avoids this writing and reading operations that are really kind of a bottleneck at the moment in current computers, as far as I understand computers. But then there's also the other thing, and that biologically systems are really tolerant to noise. So we don't have to place these things super, super accurately in this kind of physical circle. What we can do is we can actually have up to 20% of noise, and that's quite a bit. So we can really be very sloppy. And so down the line, we hope that this will allow us to build these things very cheaply, right? I mean, scaling is obviously still a problem. However, if it is really that tolerant to noise, and if you compare that to quantum computers, this is a whole different world, right? So they have to be extremely precise, but here we don't, right? And that is really amazing. And so it's very, very robust. The other thing is that the energy consumption is really on the level of biological brains per computation. I don't have the number in my head, but it's very, very low. And that's mostly because we don't have wiring, and we don't have electrons that we have to move around. So it's only photons, and they're cheap, and they're fast, and there's no wires. And so that will make this whole thing more sustainable than actually traditional electronics, and also more sustainable compared to quantum computers. And so the principle here from this navigational circuit obviously can be used to build more complex things as well. But it has to be said as well that you can always only do one thing, because you really build the algorithm into the hardware. So the hardware defines what you can do. So you can use it for a few specialized things, but those things are done extremely well. And that is a general trend in modern day computing, as far as I've read, that this concept of generally applicable things that you can use for everything, that's kind of a little bit a thing of the past. You will have very specific kinds of computers for very specific applications, but those are done extremely fast and extremely well. And so this kind of principle is useful for very specific kind of application. For example, like navigation, right? If you do kind of embed that in a tiny little drone that goes through your bloodstream or something like that, because it's so small, that can be easily done, and it doesn't use any energy, right? You can't really use a giant kind of battery to do that. So these kind of things where like autonomous like decision making is important, that's what this can do really well. And then we have to see what we can do with it if it's scalable in a way that we think. So just to completely summarize this in the end is that we have this unique combination of biology, that we extracting the algorithm from the insect brains, and we combining it with this very advanced like nanowire technology from Nano-Lund. And then we try to build this really new computing platform using this kind of nano-optoelectronic neurons and communication with light. And then we're starting with very specialized devices. We're using them to build these kind of nanophotonic neurons and compass and like sensors as well, which I didn't talk about, and like navigation circuits. But in the end, the technology we're developing like along the way here is like really energy efficient, extremely fast, and very, very small. So it could turn into a multi-purpose platform that can replace CMOS technology for some applications, not for everything, but for some things. And so maybe as a parallel approach to quantum computing, this could be useful for quite a lot of things, probably. Anyway, this is the team that works on the biology side. These are my PhD students and postdocs. This is my funding, and these are the collaborators who actually do all the nanowire technology like stuff and all the chemistry and the upscaling and things like that. And that's where the imaging of the insect brains actually was done. And well, thank you for listening. All right, you got any questions? Yes, please.
So today we have algorithms that mimic the behavior of animals, like anatomy optimizations and particle swarm optimizations. Do you think that we're mimicking the behavior, but now we can take it a step back and mimic the functionality of what's actually happening within the brains of said animals and improve those algorithms hopefully?
Yes, exactly. I think that's kind of what we can do. So I think when you're trying to like mimic the behavior of like an insect, you're kind of using kind of normal technology in order to do that. But the amount of energy you're using is a lot more than the insects like would be using to do exactly this same thing. And so there, I think we can improve a lot. So if we have a task that is very similar to what like an insect is kind of doing, and so what this kind of brain region is doing is actually vector operations. So we can do that with a lot of things, for like many different applications. And so then you can imagine that if you use that like in the same way that the hardware of the insect is kind of doing it, then we can save a lot of energy, and we can also be more efficient and faster probably, and also more robust. That's I think that's what we can do. There was another question?
The nano emitters, are they digital or analog? Do they only emit once?
No, they're actually completely analog. So they, so basically the rate of emission, so the brightness of the signal, that actually encodes your information. So it's all based on the rate-based kind of information transfer. And so you could imagine you scale it down to single photons, and then you'll be what the brain is doing in terms of action potentials, right? And you can actually count them over time. You need to integrate them, and then you have very, very, very little energy that you actually need to expend on that. But it's all completely analog, yes. Right, any other question? Yes? Oh.
Do humans have this little green section?
No. Well, so last common ancestor between humans or between like mammals or like vertebrates and insects like about 600 million years ago almost. So these guys didn't really have brains at that time. So I mean, they had probably something like a brain, but not really very sophisticated. And so it has evolved independently. There is a claim that there's some deep homology between the basal ganglia in our brain and this brain region, but it's a little bit shaky and a little bit cherry picking and probably not true, but good for grant applications. But we can cure Parkinson's when we look at the central complex, of course. But no, we don't have it. But the computational principles may also be existing, like in the hippocampus and things like that. So we have also head direction cells, like all over the brain, especially in the hippocampus. And so I mean, the ring attractor is also there. We just haven't found it yet. So they've found it in the brainstem of a fish now, like last year, and so we probably also have it in our brainstem pretty much the same way as insects have it, so with this kind of circular kind of topology of the connections. So we can learn from them and trying to look for the right things in our brains, and so essentially it'll also be there, just a bit very well hidden, like within the 85 billion neurons. And you also had a question.
Let's see if I can formulate. So bees within the hives, like each hive will have a different environment. So somewhere in the beginning of a bee's life, it has to have training on its location.
Yes.
In that specific hive. Have you seen anything like that about the training of their model, if you will, before that feeds into this part that you built?
Well, if you use this thing that we're using is called path integration, right? So basically all you have to do is you monitor how long you go into which direction, right? And that actually kind of continuously recomputes your estimate of where you are with respect to your point of origin. And so that you don't need any other information for. Bees use more complicated strategies, so they actually map their environment as well. So they can use landmarks, so they don't have to rely on path integration because it's a bit error prone. So if you go far, you accumulate kind of error and then you get it a bit wrong, and then so you use that as a backup strategy, right? But if you use landmarks and the relative location of landmarks, and you then probably like attach kind of vectors to individual kind of landmarks, then you have a much more like accurate sense of where you are with respect to your environment. And that you have to learn. And bees are kind of doing that, so they can do really amazing things. We're trying to recapitulate that in the lab at the moment, and we think we found the solution to how they do that in the blue neurons that I've shown you. These are the neurons that we think are involved in storing kind of long-term vectors and associating them with landmarks. And flies don't have those neurons, and they can't do that. So that's kind of the thing. We're trying to get into this more sophisticated like navigation regions. We're trying to actually really incorporate that into the models as well, that we have more things we can actually use for, I don't know, like autonomous cars or drones or something like that, that it can really, really map their environment, but not having to do this massive thing that the roboticists are always doing, SLAM and things like that, because it's really, really intense and lots of information. We don't want that, which is very sparsely stored information there with very few neurons. Yep, yes. Yeah, we also look at the senses. So we look at basically which information is fed through the eyes, for example, and is really ending up like into this compass system in the end. So what we know from biology is that all kinds of directional information converges like into this single bump of activity that actually tells the animal where it's heading. And this is a bit of a complicated thing, but we understand it really quite well. And so there's a convergence of idiopathic kind of cues, so your own kind of rotation. So when you rotate and you close your eyes, you still know you're rotated, and that's kind of basically a self-generated cue. And that is used there as well. So that is combined with the things you see in your environment. Actually, polarized light in the sky is used a lot in insects, for example, and the sun and all that. Yeah. For example, as well, so anything that is a stable kind of directional cue, even wind cues can be used to be integrated. As long as the wind is long enough from the same direction, you can use that and actually get a compass bearing from that, at least locally. And there's lots of information. Everything converges. Everything is super robust because it's all really multimodal. And so if you like throw away one of the cues, you can still use it. But that depends on species. And so the hierarchy of how these cues are used depends on the species' abilities and on its purpose. Like if you are a long-distance migrant, you probably don't want to listen too much to the wind because it may change way too much, but you may want to listen to, or to kind of look at the Milky Way or the stars or like the sun, kind of if you're a diurnal species, things like that. So, and then the hierarchies are different. So the overall circuitry is always the same, but how you use information, that depends a little bit on who you are. And that makes it very interesting, because if you want to build something, it tells us that maybe a general purpose thing isn't really that well suited to do like all of this. We may have to actually optimize it in very specific ways that actually mimics what we see like in the insects as well. But yeah, so we are looking at the periphery, and yeah. Well, yes, so there's a lot of attentional things that happen in the periphery. So basically, we're just looking at the middle of the brain. There's 3,500 neurons, but the insect brain is 100,000 neurons to 1,000,000 neurons. Many of them are just there for like associating information with kind of experiences and reward and things like that, but many are actually there to actually really pre-process like visual information. And how that is done specifically depends on the shape of the eyes and all of that kind of stuff. So it's very specific to the species. And there's like 1,000,000 species, we looked at like 3. So it's quite a lot to do, but then in the end, there's a lot of things. I mean, if you look at, for example, dragonflies, they actually pursue flies, and they have this attentional kind of, these top-down kind of, these processes that make sure that they can anticipate where the prey goes next, for example. Like a fly can't do that, right? So there's very species-specific things that are actually shaping the information before it reaches your decision-making center. And also your goals, obviously, are very different depending on which species you are. So if you're a bee or like a moth, if you face them with the same flower, they may behave very differently, right? Because they're interested in different things. And so how that is realized in brains is not really well understood at all. That's basically one of my big questions here. What actually mediates a species identity, right? So what makes a moth and a bee, and a fly, right? And so that we can learn from for technology as well. So if you go away from this general purpose technology and try to get into specializations, then I think it's very important to learn from how has nature achieved these specializations, and can we harvest some of that to make our technology more kind of dedicated to a specific task, and thereby make it more sustainable, because we can throw away everything we don't need and we just focus on the stuff that's needed for the specific task of that piece of technology. Right. I think we went over time already, right? But any more questions? And thanks for all the questions. That's really nice.